Good morning. We have one more class on rotational motion, rotational forces, torques, accelerations, so let's do this. I hope this is working well. I feel like we're doing a really thorough look at the chapter. I'm hoping we have a pretty good pace and we have some good examples that are clearly showing what these different physical quantities mean. We had finished up the last class. I wanted to go back and look at a couple of examples. Example 1010, pulling a bucket, really good example, one worth going through pretty thoroughly, looking at linear motion and rotational motion and how we can bring that all together in a combined system. And then that last example that we looked at, looking at a rotating stick, and realizing that different parts of the stick, the axis, oh look, I wrote axis twice. I wrote axis there, I wrote axis here. That's the axis that it's going to spin around. We said this could become a amusement park ride where we could seat people depending on what extreme acceleration they want to undergo. And we could map out, the acceleration we said would depend on how far you are away from the axis. And then we were able to go in and determine what the rotational acceleration would be by looking at torques and dividing through by rotational inertia. That is the fundamental equation for figuring out motion of these rotating objects. Find out how much torque there is, determine the rotational inertia, and that formula told us that the rotational acceleration then would be 3/2 g over d, where d was the length of this rod. And then we looked at a spot way out at the edge and said r is equal to d. And then we plugged in the acceleration value and found out that accelerations along this amusement park ride go all the way between being 0, somebody at the axis just rotates over, versus someone at the edge that at least initially is accelerating at 3/2 g. All right, so here's a set of suggestions that they give us for solving problems in rotational dynamics. And look, it's number one again. It's always number one. Draw a diagram. 2 looks familiar too. Determine what the system is made out of. So let's see. Diagram. What's this system consist of? It consists of a stick, right? And then there's an axis of rotation. What about this one? Well, this system's got 2 objects. We got the pulley, and we've got a bucket, and we had to include both. Okay, so draw a free body diagram for each of the objects. Now you can put all the objects, well, we did this before. If you've got a series of linear objects, you could put them all together. Here we tend to have some objects that are rotating, some that are in linear motion. So we really need a separate free body diagram for each. And then identify every force acting on it and the location of where they act. So we've been mostly pretty careful about identifying where forces are acting, but now it just becomes crucial. We've got to keep track of where the force is acting because we need to be able to measure lever distances. So once we find the axis of rotation, we will find out what the lever distances are, and that will allow us to go in and calculate torques. So we want to be able to get torques figured out. Now, for Newton's second law for rotation, we're going to have to be looking at torques, and we're going to have to be looking at rotational inertia. So we need to find out some formula for the rotational inertia when we do this. Apply Newton's second law as needed. Solve, check your answer for units. So a lot of the same stuff. It's just that we now have rotational diagrams. All right, what we want to do now is come back and take a bit of a closer look at rotational inertia. We had that really basic formula, mr squared. And then what we want to do is we want to try using the integration formula. So in the integration formula, we break the object into a bunch of pieces, each individual piece having mass dm, and then we have to find out how far that individual piece of mass, how far is it located from the axis of rotation. So that's the formula. It's easy enough to write this formula down. How do we use it? So we're just kind of jumping in with a fairly detailed example here. It's a cylinder. Now, the cylinder could be hollow, or maybe it's not. So I think the solid cylinder is easier, and then maybe we'll come back and look at the hollow one. For the hollow one, we've got two radiuses we have to keep track of, R1 and R2. If it's a solid cylinder, then we can set R1 equal to 0. Now, the cylinder also has a height, so we want to keep track of the height over here. And what they want us to do in the first part at least is show that the moment of inertia of they start with the hollow cylinder. That's the difficult one. I'm not sure. What do you think? Should we start off with the difficult one, or should we start with the easier one and then work our way up? Either way, the calculations are going to be pretty similar. They say, show that for a hollow cylinder, the formula comes out as 1/2 m r1 squared plus r2 squared. And then on part B, it says, use this formula to come up with the inertia for a solid cylinder. Okay, so here's what it looks like. Here is that cylinder. And so the cylinder goes around like this. I've got an inner radius of R1. I've got an outer radius of R2. And then what we want to do is consider all the R values in between. Now in their diagram, they're using big R as a variable, and then using the thickness here as dr, d big R. I'm going to use little r. That's been kind of, that's a convention that I think we will stick to with our integrations. So I'm going to use little r for variable r. R1 and R2 are kind of constants that are fixed. And then this would become dr, d little r. So here we go. Here's the formula. I is equal to little r squared dm. Now, what I can do is I can break this cylinder into a series of hoops. So I can go one hoop at a time from R1, and then I can go to a hoop just a little bigger, just a little bigger. Each one of these hoops is going to have a thickness of dr. And each one of these hoops is going to be located a distance little r from the axis of rotation. So what we'll say is if the material that this is made out of, if it is uniform density material, then what we can say is that the mass contained in one of these little thin circular hoops is proportional to the total mass, it's a certain fraction, as the volume is to the total volume. This is kind of a standard calculational approach or integrational approach when we have something with uniform density. We can say that the portion of mass contained in each little infinitesimal piece compared with the total mass is the volume in that infinitesimal piece compared with the total volume. Now, the volume of that circular ring is going to have a thickness of dr. It's got a distance all the way around that's 2 pi r. And then if you remember, if we do a side view, it has a thickness of h. And so the total volume there is 2 pi r h dr. Now I'm hoping you guys are far enough along in Calc 2 that you've started seeing some of these. If you're not quite sure how these work, stop by office hours. We can get that looked at in more detail. So the total volume of a hollowed out cylinder would be pi r2 squared minus pi r1 squared That's kind of that cross-sectional area, times h. So the height, again, comes into this. Now notice that when I do this ratio of infinitesimal mass to total mass, infinitesimal volume to total volume, the h's cancel out. It's really that cross-section that we're interested in, just because this thing has a bigger h value, that contributes an equal factor to the individual strips and to the cylinder as a whole. So the h's cancel out, and I can move my factor of m over here. It says that each circular cylindrical strip is going to be, the dm for that will be big M times 2r dr divided by big R squared, big R2 squared minus big R1 squared. The pi's canceled out, so I'm just left with the 2 from the circumference formula. So that's it. So these are good examples of developing skills in setting up integrations. And then we got, so once these pi's have canceled out, it's hard for me to see where that came from. So, it's really good to get these intermediate steps in here. This is an infinitesimal volume. This is the total volume for that cylinder shape. All right, so that dm, we've spent a bit of time getting that set up. This dm that we've got the formula for now slides right into the integration. And then I've got 2 additional factors of r, because that's what we showed rotational inertias will have. So it's going to depend how far we are. Now the rotational axis here goes from the center, or comes down from the side view, comes down right through the center here. From here the axis is coming from above down through that. So plugging that in and pulling out everything I can from the integration, I was able to pull out factors of 2 and m. And then these R2 squareds and R1 squareds, those are constants. That came out. What was left inside were 2 factors of little r, based on the definition of a rotational inertia, and then a 3rd factor of little r from the circumference effect. So as you get the strip inside, is going to have the least contribution, and then the strips as you move out, the circular cylindrical strips, are going to create ever-increasing rotational inertia because they are farther away from the axis and they're bigger. The circumferences go up, as well as the r squared factor for the inertia. That gives us 3 factors of little r, which we integrate from r1 to r2. That gives us, when we carry out that integration, that's 1/4 r to the 4th, evaluated between r1 and r2. When we plug those in, we're going to get a factor of 1/4. We're going to get a factor of r to the 4th minus r to the 4th, which is a little distressing because that's not the formula they gave us, but then we realize, oh, that's the difference of 2 squares. Well, this is the difference of 2 squares also. But this is the one we want to work from. That can be set up as r2 squared minus r1 squared times r2 squared plus r1 squared as a difference of 2 squares. Now why that's so useful is this part cancels exactly. Now is that a coincidence or what? And so the entire formula, the rotational inertia formula for this hollow cylinder, reduces down to 1/2 m r1 squared plus r2 squared. And sometimes people look at that and they go, why is it plus? Well, that's the term that got left here. Let's see if it makes sense. Now, if we solve this with a cylinder with two radiuses, meaning that there's a section in the middle that's been cut out, how would we take this formula and turn it into a solid cylinder? And you go, well, if it were a solid cylinder, R1 would be 0. So if R1 becomes 0, well, the formula becomes 1/2 mr squared. And that is the formula in the table. So that's encouraging. It seems like we have the right, well, we know we have the right formula. because they told us what the answer was expected to be. But that worked. And then how could we recover the formula for the hoop? Now for the hoop, let's think about this. If it's a hoop, R1 and R2 are both equal to essentially the same R. And then we've got all the mass somehow concentrated in that thin hoop. And if we do that, then we get the formula for a hoop. So yeah, this works. We can turn it back into a solid cylinder, or we can turn it into hoop as needed. All right, what happens if we're rotating an object and it's not around the center of mass? What if it is around a different location on the object? Is there a way, do we have to go back and redo the integration? Because, so for example, the example we just did, well, it was manageable. It took some doing. But what would happen if there was instead of the axis going right through the center, what if the axis was here? Or the axis was out here, so this whole thing is going around an axis along one of the edges. I would not want to go in and integrate that. Well, it turns out that there's a very handy theorem, the parallel axis theorem. We're not going to go through the derivation. I'm trying to remember if the book does. I think it does. What it shows is if you can identify, if you can calculate the rotational inertia through the center of mass for an object, you can then calculate the rotational inertia at any other axis parallel to the axis that you've already calculated by adding the mass of the object and a distance squared. This seems almost too good to be true. It means this. It means that, let's say that we've gone through and we did the integration for a solid cylinder and we found out the rotational inertia is 1/2 mr squared. And so we've got that figured out. But now somebody wants us, instead of this nice axis that goes through the center of mass and lots of symmetry, they want us to move the axis, it's parallel to where it was before. They want us to move it over a distance h parallel to where the center of mass location was. That's going to be a miserable thing to integrate, but the parallel axis theorem says you don't have to do the integration. As long as the new axis is parallel to the center of mass axis that you've already calculated, you just add on mh squared. So let's try this and see what would that be. Now, we can already tell that the lowest rotational inertia will be the axes that go through the center of mass, right? Rotational inertias are going to depend on how the mass is distributed around the axis. And if I go through the center of mass, that's kind of getting as much mass as possible close to the axis. Notice when I move the axis out to here, here is my new axis here. It's now axis A. If I rotate this whole thing around that axis, much of this cylinder is going to be very far away from this axis. The rotational inertia is going to be higher. And it's going to be higher by an amount mh squared. Now if we go from to the center of mass, and we just looked this up, actually we just solved for this. The rotational inertia there was 1/2 mr squared. And what we can do now for axis A is take the center of mass value, the 1/2 mr squared, and add on m times h squared. Now, in this case, how far did we shift the axis over? And we shifted it over right to the edge. So h in this case is r. It could have been 1/2 r or 1/3 r, 1/4, but in this example, they're asking what would happen if the axis went all the way out to the edge. And so the rotational inertia there is 3 times larger. Not a surprise when you play around with these problems and see how much of an effect this will make. So 3/2 mr squared will be the rotational inertia around that edge. Now there's another theorem that we don't use quite as often. This one's also interesting. It's got more constraints on it. It only works for objects that can be considered to be flat. So here what we've got is we've got a flat disk, and it says that this is the perpendicular axis theorem, so it kind of a matching set here that they've got. The rotational axis, the rotational inertia around the axis perpendicular to the flat area is equal to the rotational inertias around the two perpendicular axes going through the object. So for this, for example, because of the symmetry, we can say, well, Ix and Iy, they've got to be the same thing. So here's the setup. Iz is equal to Ix plus Iy. We'll turn this into an example. If I've got a flat disk, then Iz is equal to Ix plus Iy. Well, these two guys are equal to each other because of the symmetry. And that says that Ix is equal to Iy, and they're going to be 1/2 as large as Iz because added together, adding these two equal amounts gives me Iz. So that says that Iz then, if Iz is 1/2 mr squared, which it is for a solid cylinder, if we take a solid cylinder and rotate, switch it over by 90 degrees, that is going to have a rotational inertia along the x or y axes of 1/4. Okay, now remember it has to be flat, so this will work in the limit where the thickness is really, really small compared with the R value. But that shows up occasionally, okay, not as much. Only works for flat objects, but still, it's better than going back and redoing an entire new integration. We can move the axis of rotation around, we can even rotate it. So, this is probably a good time to point out too, if you look at all these rotational inertias that we've looked at, there are always rotational inertias around axes with a lot of symmetry. So when we don't have a lot of symmetry, and we'll see some examples in chapter 11, when we don't have a lot of symmetry, it's harder to go in and calculate all of the effects. If we have an object that's just rotating freely, these are referred to, the axes we have here, are referred to as the principal axes of rotation. So objects will have principal axes of rotation that are stable, but they could have other axes. If we had an axis of rotation that was diagonally set here, and we spun this object, it would tend to move away from that axis of rotation. So only the principal axes of rotation are stable, and it turns out not even all of those are stable. So for an object will have one or two principal axes, of the three, an object will have three, in general, three principal axes of rotation, and one or two of those will be stable. Okay, so rotating objects are tricky. And we're through this, so let's move on. All right, let's take a look at kinetic energies. So we're kind of following the same path we did with linear motion. We did all the kinematics, right? Remember all the kinematics that we looked at? And then we did forces, and then we did energy and momentum. Well, for rotation, we did all the kinematics. We've looked at the forces, which we call torques, and mass, we call rotational inertia. Now we're ready to look at energy. So let's introduce kinetic energy. Now, for an object that's rotating, what we could do is we could take the object, break it up into a bunch of little pieces, and add together all of the 1/2 mv squares. Now, when we do that for a rotating object, what we can do is show that the rotational kinetic energy, the kinetic energy of an object rotating around an axis, is given by 1/2 rotational inertia omega squared. That's kind of a miracle, right? That's amazing. What was the kinetic energy formula we learned back in chapter 7? And that was 1/2 mv squared. And now we're saying for a rotating object, it's 1/2 rotational mass times rotational velocity squared. It's a complete analogous formula. So it should be easy to remember that one. If I can remember 1/2 mv squared, I can remember 1/2 I omega squared. Now, for an object that is both rotating and translating at the same time, we can add those together. We can add together the kinetic energy of the object, typically around its center of mass, and then we can add on to that its rotational energy. Again, often it's around the center of mass. It turns out that there's a little flexibility here. We'll see how this works. We can actually pick different axes of rotation when we're combining translational and rotational kinetic energies. All right, so let's get back. I think we had talked about this briefly before. If we have an incline and we have different shapes, objects, here's a hoop, here's an empty can, that's kind of like a hoop. Here is a solid cylinder, here is a sphere, and here is a box. Now, we got to be a little careful about this. That box is only out ahead because we're assuming it's frictionless. And yet, if the surface is frictionless, everything just slides down. What happens if we have a completely frictionless surface and we put a cylinder at the top and let go? The cylinder slides down. If we put a sphere up there, the sphere slides down. So there's nothing to set rotation into motion unless there's a frictional force. So we really got to decide, are we going to have friction or not? Maybe it's an unfair comparison to say, hey, the box gets to the bottom first if there's no friction. Because if there's no friction, everybody gets to the bottom at the same time, it turns out. What's holding up these other objects, what's slowing them down, is that some of their kinetic energy is now rotational. So they've started to rotate, and because they've invested some of their energy into rotation, there's not as much energy left as linear kinetic energy, and they just don't go down the incline as fast. So it says now, let's imagine all these different shapes. Let's take the box out of it for a minute. So I'm just going to stick with these objects and then put friction back in. Let's say that they all have the same mass. Not that they need to. We're going to come back and see what really is important here. But let's have them all have the same mass. If they all have the same mass, then they all start off with the same amount of potential energy. So if this is an energy calculation, what we can do is say there's a certain amount of potential energy that we start with, and by the time we get to the bottom, all the potential energy is now kinetic energy, and we can use energy conservation to find out how fast they go down the incline. So now let's take a look at a rolling object. So if we do this, if we have an object that's rolling, then we can say that the speed at which the center of mass is moving for this rolling object is given by r times omega, where omega represents the speed at which this is spinning around. Now, in the reference frame of the outside world, this object is rolling and it's making its way to the right. But you could also move into the reference frame of the wheel, and that's often very handy, right? If I'm watching a car drive along and I'm watching its wheels rotate, it's got rotational motion and it's got linear motion. But if I move right alongside the car as the wheel rotates and I'm staring at it, in my reference frame, all it's doing is rotating. So depending on which reference frame we're in, we can find a reference frame that removes the translational effect and only leaves the rotational kinetic energy. Now let's move back into the frame where the thing is rolling along. What we can do then is what that previous slide suggested, is we can write in the translational kinetic energy, and then we can write in the formula for the rotational kinetic energy, and we can add them together. Now, the formulas have different variables in them, is there some way we could combine the m's and the v's and the i's and the omegas to simplify the expression? And we can. What we can do is we can say that the rotational inertia around the center of mass of this rolling cylinder, sphere, hoop is given by c, the shape factor, times mr squared. Now if it's a cylinder, c is 1/2. If it's a hoop, c is 1. If it's a sphere, c is 2/5. But what we can do is we can take specifically the rotational kinetic energy expression. For I, I'm going to substitute in cmr squared. For omega, I'm going to substitute in v over r squared. And then look, all the r's go out, and the rotational kinetic energy can be written for these objects, for a round object with the shape factor, as c times 1/2 mv squared. That's it. So the r's cancel out, which is really handy, because now what I can do is say, all right, the total kinetic energy is given by 1/2 mv squared plus c times 1/2 mv squared. It's 1 plus the shape factor times 1/2 mv squared. If it's not rolling, then the shape factor goes out. And then it's the sliding box on a frictionless surface. But if it is rolling, kinetic energy, some of the kinetic energy is going to go into rotational kinetic energy. So we can keep track of the rotational kinetic energy by seeing where the c factor, where the shape factor, shows up in the formulas. So let's follow it and see. So what we're going to do is say, here is this rolling round object, and there's a kinetic energy of rotation that is okay. This is important, so let's go back and take a look, because I want to draw this distinction. On this problem, where was the axis of rotation? And on this example, the axis of rotation was at the center of the rolling object. So we did the rotation around the center of mass, and then we added on the linear, the translational kinetic energy. But there's an alternate way to look at this, and I mentioned this before. This is kind of intriguing. What if we move the axis of rotation from the center to right there? Now, in reality, is it really rotating around this point, or is it rotating here? I mean, I know that if we move right along with this wheel as it rotates, it's going to look, you know, in that reference frame, all it has is rotation around the center of mass. But in this reference frame, where the round object is rolling, what it's actually doing is it's tipping around that point. That point is motionless just for an instant while it rolls just a little bit, and then a new contact point lands right there. It's not sliding, so every time a new contact is made, that becomes, just for an instant, an instantaneous axis of rotation. So what if mathematically we set it up so that it's only rotation happening? It's rotation around this axis. Well, then what we would say is, okay, in this approach, all of the kinetic energy is kinetic energy of rotation. Kinetic energy of rotation is 1/2 I omega squared. Omega is still given by V over R. What happens with the rotational inertia if instead of an axis of rotation here, we move the axis of rotation in a parallel fashion out to the edge? Well, the center of mass, rotational inertia, was c times mr squared. And the parallel axis theorem tells us if we now shift that rotational inertia a distance r, that the rotational inertia around the edge will be the original rotational inertia around the center of mass plus an additional mr squared. Now, when we add that in, that means an m, doesn't it? Somehow this m got dropped out. Make an m go back in here. So there's an m right here. I don't think that's easy enough to correct. So I'm going to get CMR squared plus MR squared, and that works out to be 1 plus C MR squared. When I take this new rotational inertia for the new axis that we're working in terms of, and put that into the rotational kinetic energy, now we're saying the very same formula, the kinetic energy is 1 plus C, 1/2 mv squared, but now all of it's rotational. So you can see it's a little weird, but it's a little bit arbitrary as to how we divide up the kinetic energy to rotation and translation. We could have all the kinetic energy be rotation, or we can have part of it rotation and part of it translation. And we get the same answers as far as how much total kinetic energy is present in this rotating object. All right, we are ready now. So here is that incline. We've got a round object up here. We don't know what it is, so we're going to use the shape factor. It could be a sphere, it could be a hoop, it could be a solid cylinder. We're going to start at point A and we're going to drop to point B. We're going to take the kinetic potential energy, the gravitational potential energy at point A, and set it equal to kinetic energy at point B. So the gravitational potential energy we start with will be mgh. Now that doesn't have to do with rotation or translation, it's just where is the object located. And so the center of mass of this object, when it goes from point A to point B, the center of mass will drop by a distance h. And so that's what goes into the potential energy. Now, the kinetic energy formula, we decided we could either write it as partially translational and partially rotational, or we could write it all as in either approach, we ended up with this. So if I solve this now for how fast am I going as I drop down the incline, the speed that we're going to reach by the time we get to the bottom is going to be given by 2gh divided by 1 plus the shape factor. So everything else canceled out. The mass is canceled out. So it turns out it doesn't matter what the mass is. If you got a big sphere or a little sphere or a tiny sphere, they're all going to have the same velocity when they get to the bottom. Same thing with the cylinders and the hoops. It depends on what the shape is. So the masses did cancel out, but the shape factor does not. And so that says that at the bottom, the object with the smallest shape factor is going the fastest. So the sphere is going the fastest, the cylinder is going not as fast, and the hoop's going the slowest. So for this particular example, does it depend on the mass? No. Does it depend on the shape? Yes, it does. The m's canceled out right here. So there was an m in gravitational potential energy, specifically because it was gravitational potential energy. And the m's canceled here. The inertial m's from the kinetic energy canceled out. Okay, kind of interesting. Now what about that sliding box with no friction? Then we just ignore the c because nothing is rotating, and the speed at the bottom is going to be square root of 2gh. That might be familiar if you think back to some of those problems in chapter 3 and 4. That was a number we would get when we rolled things down inclines. Or maybe in the energy chapters also, 7 and 8. Okay, kind of an interesting, I hope, an interesting example. All right, let's do this. Okay, so we're getting into these examples with these inclines, and I think these are really useful for thinking about, well, rotational kinetic energy. Now we're going to go back and look at another example in terms of torques and forces. So let's go back to a diagram that looks kind of like chapter 4, maybe chapter 5, because we do have friction. And here is a rolling object. There's a normal force. There are two components of gravity, sine theta and cosine theta. There's a static frictional force. Now the static frictional force here is important because without that, the thing just slides down. With the frictional force, if there's enough friction, then it won't slip. And the round object will go into a rolling pattern. So what we can do here then is let's analyze this force diagram. If I'm looking in this perpendicular diagonal direction, the normal force has to match up with mg cos theta. There's no acceleration taking place in that direction, and so I can set those two forces equal to each other. Now, I'm guessing this thing is going to roll down the incline, and so there's going to be a velocity associated with that, and there's going to be an acceleration. Now, velocities and accelerations, they're not forces, so I'm going to put those off to the side a little ways. Now, when I get ready to write down my acceleration equation, the acceleration is the direction going down the incline, and that's going to be given by force mg sine theta, so mg sine theta here, minus the frictional force. So that frictional force is reducing the acceleration. Okay, so what is it? What are the forces that actually cause a rotating object to accelerate at a lower rate? And it's friction. So friction is being used to spin up the object. We're going to get this object rotating, and so that frictional force goes in and divides through by m. Now, we could do this. We could say that the static frictional force is going to be somewhere between 0 and some maximum value, and so as long as the maximum value is large enough, the object won't slip. We can actually go through and determine just how large the frictional force would need to be. We could calculate a coefficient of static friction that would be needed. All right, so let's look then for this one object that's rolling. What we can do is say that it's got both rotational motion, we'll look at torques, and it's got linear motion. We will look at forces that we have right here. Okay, so this is the formula that we have for the linear acceleration coming down the incline. Let's ask what's happening rotationally. Because what I've got right now is I've got this static frictional force, but I don't know what that is. It could be anything between 0 and some maximum value, so I don't know what the static frictional force might be. I've got to find a way to solve for it. So let's go use our rotational formula. Alpha is equal to torque divided by rotational inertia. The torque here is going to be, well, let's take a look and see. If we're thinking of the center of mass, so let's use the center of, and that's what it says up here, Cm. We're using the center of mass on right now, currently, in solving this. And the center of mass is right here. The normal force, the gravitational forces, both pass right through the center of mass. They're not going to give me any torque. And so the only torque around the center of mass is going to be given by the static frictional force times the lever distance. Now the rotational inertia is going to be c times mr squared. All right, well, we're using the same c values for the hoop and the sphere and the cylinder. So what we can do is write in the torque and then write in the rotational inertia. The r's look like they're getting ready to cancel here, and then I can say that in terms of rotational motion, the linear acceleration is r times the rotational acceleration, and that gives me another factor of r, and the r's cancel. I'm only left with static friction divided by Cm. So that says that the static frictional force is going to be that large. The static frictional force is going to be Cm acceleration. It needs to be that large. If it's not that large, it will start to slip. But now I have an algebraic expression which will help guide me. So what we can do then is where we were stuck with the frictional force. I can now take in this expression for the frictional force, which I got by analyzing the rotation. I bring that up to here, and my formula now looks like this. The masses will all cancel now. I've got a factor of m in each one of those. And when I solve for the a, the CA term comes over to this side, the g sine theta stays here. I'm getting an acceleration that is g sine theta over 1 plus c. So using energy conservation, we solved for the velocities, but using forces and torques, we're going to solve for the acceleration. So that's the acceleration of the rolling object. And the accelerations will not be the same. The accelerations do not depend on mass, but the accelerations do depend on the shape. Now, what's the connection between the acceleration we've calculated here and the previous example, where we were looking at velocities using energy conservation? Well, for constant acceleration, we can say v squared is equal to 2a times distance. So if I take this expression and substitute it in and solve for velocity at the bottom, I get the same expression back. So that's a good thing, that solving using a force diagram, using forces and torques, gives the same result as using energy conservation. So that's encouraging. And again, what we're showing is the bigger the c factor, the smaller the acceleration of the object. It's going to have as much kinetic energy, but with a bigger c factor, more energy goes into rotation, and that doesn't get you down the ramp faster. Okay, so more of the energy ends up getting diverted to rotation on the way down. Now we can come back and use the other axis. Remember before when we did energy analysis, kinetic energy formulas, we said instead of using the center of mass, we can use the contact point as an instantaneous axis of rotation. It seems really crazy. You know, it seems often in physics there should be kind of one correct way to do the problem, but it turns out you can show that using the laws of motion and bringing rotation into them, we can either use the contact point as an axis, or we can use the center of mass, and they work, either approach. Let's see if we get the same thing here. So if we use this approach, where we're actually looking at rotations around that point, friction is no longer the torque, mg sine theta is the torque. So that seems kind of funny too, but mg sine theta and friction are what we consider a force couple. So they're two forces in opposite directions displaced away from each other. So what we know is that two forces displaced from each other will create overall a torque. But it's not necessarily we have to assign all the torque to one or the other. So what we've done is we've shifted over, and now we're going to have mg sine theta not be the torque, sorry. Mg sine theta is going to be the torque. Friction is not, because friction is not, does not have a lever around the axis that we are now looking at. So the torque then can be written as the force times the lever distance. Now the rotational inertia has changed. Because we move the axis away from the center of mass, we have to use the parallel axis theorem. And the parallel axis theorem tells us that we're going to have c plus one additional mr squared. So it's kind of the same thing we did before with the energy approaches. So we're doing, we did the energy conservation approach using the two different axes, the center of mass and then the contact point. And now we're doing the same thing with forces and torques. We solved it around the center of mass. Now we're coming back and solving it for rotations around the contact point. So the rotational inertia goes up. And when we solve the acceleration here as r times alpha, we get g sine theta over 1 plus c. Oh, this approach was faster because we never had to go back and do a linear formula. We never went back and used the linear formula on this. Everything was done exclusively from the rotation. Remember the problem we had before when we were using the formulas on the previous page is that we didn't know how much frictional force there was. We did not have a good way to solve for it when we were looking at the center of mass, so we had to go through a couple of different force diagrams. But when we used this approach with the contact point, the static frictional force didn't show up in the equations because it was taken out because the frictional force went right through the axis of rotation. So we got the same answer. So the acceleration looks the very same as it did before. Put some numbers in. If theta is equal to 30 degrees, any sphere, not just, doesn't matter what, notice what's missing here, what's not in the formula. What's not in the formula is r, and what's not in the formula is m. So any sphere, any solid sphere, on a 30-degree slope will have an acceleration of 3.50 meters per second squared, and that's from using the formula over here. So the c factor here was 2/5, and in the denominator I have 1 plus c, which makes that 7/5. Bringing it up to the numerator, it becomes 5/7. For the cylinder, I put in that the shape factor of c equals 1/2, and when I carry out the same calculation, I get 2/3, and for the hoop, I get 1/2. So again, the nice feature of the shape factor is I can carry the shape factor all the way through. And then when I get to the end, I can see what the dependence on specifically the shape factor will be, and that works. So you can see from calculations the sphere and the cylinder and the hoop and how their accelerations will compare. All right, if we're going to have kinetic energy in a rotating object, I guess we need to go back and talk about work. How did the energy end up in there? And work was done, if you remember back in chapter 7, it was a force times a displacement. So in angular terms, work is done by a torque with a rotational displacement. So, and then to make the equations match up even a little better, I did kind of my own diagram here. So here's that picture, and what we're doing is we're exerting a force over some distance, s. So the force is being exerted, and by the time I have exerted my force over a distance s on that object, the work we've done to speed up the object is F times S. Well, I can write that as F times R and S over R. I put a factor of R here and a factor in the denominator here, so it's the same thing. Well, F times R is torque, and S over R is the angular displacement. So what that says is, when I'm integrating work as F ds, that can be written as torque d theta. So torque d theta is a way to determine how much work is being done. Now, that's in terms of, to do this, I need to know the torque and I need to know what the displacement is, but that's a way we can go in and determine how much rotational work has been done. Now, the work will also show up as kinetic energy. And so I could also look at the kinetic energy and work from that instead. All right, so we had looked at rolling objects. There's a few more slides here talking a little bit more about rotations. So let's take a look at those. It says in picture in A wheel is rolling without slipping. When point P comes down, it touches the ground and it doesn't slide. So the tire comes down and touches that one point. We talked about this a little bit. So it's instantaneously at rest. And the velocity of the center of mass, if you follow the center of mass location on this wheel, the center of the wheel actually, you find that it's moving, it can be moving at a constant velocity. Even though individual points on the wheel, the point at the top is going at twice the speed, and a point at the bottom is instantaneously at rest. So we can add together translational and rotational effects. Now, B is looking at a different reference frame. So in the other reference frame, the pavement is going to the left with velocity v, and the wheel is just staying in one place. And that's an easier way to analyze what's going on. So the linear speed of the wheel is still related to its angular speed. V is equal to r times omega for this particular setup. Okay, and then they ask the profound question, why does a round object, a rolling sphere, slow down? So this should probably be in a philosophy class or something, right? Let's see, a rolling sphere, why does it slow down and stop rather than roll forever? Shouldn't we be able to get a sphere that just, once it starts rolling, and we keep things level at the same elevation, it just rolls and rolls and rolls and rolls? Now, a common thing to say with this is friction slows it down. It's not really friction, right? What's happening here is, as it's rolling, there's got to be some kind of a force pushing back on it. But remember, at the contact point, when that part of the wheel comes down and hits, it's not moving at that instant. It doesn't slide along the surface. So there's not really a frictional force pushing it in any particular direction. And gravity is not exerting a torque. Normal force is not exerting a torque. So it would seem that in the limit, where it's a perfectly uniform sphere, uniform density, and a perfectly level surface, it should roll forever. But here's what happens. So what will happen is elasticity in the materials. So there's going to be some combination of the round object and the surface. They're not going to be perfectly rigid. So the bottom of the sphere in this picture has deformed a little bit. And the pavement has deformed a little bit. And as a result, we're not getting that contact point being right at the bottom. And so as the wheel, as the round object, makes its way rolling along the surface, it has to push down on the pavement. So it's this force that's coming as a result of deforming the spherical object. So how do you get around this? And you get a surface that has no elasticity, right? You get something that's just a solid stainless steel surface or something, and then you get a wheel that also is just stainless steel. Or if it's a bicycle tire, you pump the tire up to an incredible pressure, right? You get the tire pressure really, really, really high, so you're not getting all this rolling resistance. So, most people riding around on their bicycles don't have their tires pumped up to adequate pressure. You guys have probably noticed this. You look at the tires and you go, oh my gosh, this says 40, 50 pounds of pressure. I've got like 15 in there. And, when you get up to the pressure you're supposed to ride at, that removes some of this deformation, and it does away with what we call rolling resistance. So the rolling resistance goes away, or it's reduced if we go to surfaces that are more rigid. All right, that wraps up Chapter 10. That was a lot. Chapter 10 has a lot of stuff in it. So, and again, I hope we went at a good pace so that things are making sense. I know it's going to take a few passes through the material to make sense. It's not like one pass through and everything's making sense. Rotational motion is tricky, so allow yourself some time put a good amount of time into looking through what we've talked about here, and look at the examples, look at the homework examples, questions that come up, stop by office hours. There's a couple more slides here, but this is summarizing what we just went through, and that was traumatic, so don't want to do that again right away. All right, anyway, if you guys have questions, stop by. Remember to rotate, get a lot of practice rotating. There's nothing like practicing all this rotational stuff. When you're walking along, just spontaneously go into rotational motion and try some of these things out.